This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, good afternoon. We will continue. So after a low pass filter, we will be checking the ADC specification. So when you get the ADC, then this is one example, ADS 830. In this ADC you can see it's a 8-bit. So the output you will have 8 lines, 8-bit. Then when you see the block level diagram here, in most of the ADCs you will see something like this. When you have especially high resolution ADC. So when the ADC, when it is high resolution, means it got a higher number of outputs, 16-bit higher resolution, than 8-bit is low resolution, 12-bit is better, 16-bit means higher resolution. So resolution means it has more number of bits. So that is a resolution. We will study ADC later. But when it comes to ADC, so this is your input. And then here they said D0 to D7. So that's the reason 8-bit. But input, when it comes to input, ADC got 2 inputs. So it got a non-inverting input and inverting input. So then they have put in the bracket that is optional. So why we need is when you have noisy signals, even the low pass filter will not be able to prevent all the noises. You will see the design complexity. In that case, ADC manufacturer recommend you to use in the differential mode operation, because we know the differential mode. Differential mode means the same signal, here is a positive, then you have to make it negative and then connect here. In some cases, sometimes what happens is the differential is much better. Even after the low pass filter you will have the noises. Then how will you convert? So in that case what you need is if you are using a differential channel, well, in your DSO you don't need to use a differential. But in future if you are using differential, then you have data sheet like this. This is an example, 650 megahertz differential ADC driver bar dual selectable gain amplifier. So here what it does is, if you got a single-ended input, it will make it differential, see. So this is something like this. So you got only one input. In the output you have 2. So if you connect a signal like this, and then what it does is it will amplify, and then you will get 2 inputs like this. So then you can use it. Then you buy this IC and then you can connect. See, there they said connecting to an ADC. See if you zoom in, you can see this is connecting to some 14-bit ADC, 80 mega samples per second. So this you keep in mind when you want to use high resolution ADC. Means you have very small noise, because high resolution means when you have 16-bit, your 1-bit resolution means the one bit is maybe in millivolt. So if you got noise, then your ADC output will be jumping. So in order to prevent that, we can use in differential mode. But in your case, it is 8-bit. You are dealing with low frequency, so we don't need this 2. You don't need a differential. Then they said it's anyway optional. If you want, you can drive in differential. For the DSO, we will be using single-ended operation. Single-ended means we will be using only one input. So that is the reason when you read the data sheet, So I am going to zoom in. See, standard single-ended range, optional single-ended input range, that is the optional second one, common mode voltage, optional differential input range. So these are the main thing, optional differential input range or standard single-ended input range. So if you are using standard single-ended input range, means you are using only one line. In that case, they already said your minimum voltage is 1.5, maximum voltage is 3.5, because that is the only range ADC will accept. If you are using differential input range, they already said 2 volt peak to peak, means your minimum is 2 volt, maximum is 3 volt. So what it means? So that is very small. So what is the meaning? So we are using for DSO single-ended. We don't need additional complexity. We don't need a single-ended to differential converter, and because we don't need to use that one, because it's a low resolution ADC. And then 1.5 to 3.5 means what is the difference? 2 volt. So what ADC wanted is see. So 2 volt range means your voltage range is minus 5.6 to plus 5.6, that is the range. This range ADC will convert between 1.5 to 2.5. You know what I meant? So this range, big range, ADC will convert into 2 volt range. So ADC, so you have to convert. So your minus 5.6 to plus 5.6 range in the ADC, that will be 2 volt range. That is, as you know, that's what ADC is going to do. Then you already decided standard single-ended input range. So we already decided. Then ADC manufacturer gives you how to make it, because they don't want people figuring out. Then nobody will buy their ADC, because you have to design the circuit and test it. So they design and test it and give you. See, there are so many examples. If you are looking for AC coupled input configuration, see, this is the ADC. And then AC coupled, see, they use a capacitor. But for DSO, we don't need AC coupling, sorry. See, AC coupled application, see, here you got a capacitor. So we don't need a AC, no, DSO, no. AC coupling, dual supply amplifier, some other application. Again, see, AC, no. Then we need DC coupling. Then, so when you come here, DC coupled interface circuit with the dual current feedback amplifier OPA 2681, and then OPA 2680 can be used in place of this OPA 2681 if a voltage feedback amplifier required. So you don't have to, they are giving lots of options. So here, is it a single-ended or dual-ended operation? Single-ended, because here is only one input, and then here the optional input ADC, they already said how to connect it. So if you are not using, so the other optional input, then that is connecting to your common mode in the ADC pin number, and then will be connecting to a capacitor to 0.1 microfarad and then grounding. See, that's how we will be doing. Yep, see, like that. So then they already said how to connect it, and when it is connecting, sorry. Yeah, so they already said how to connect it. Yep, so they already said how to connect it. So this is a V input, is a single-ended. And then they already said how to make the scaling network. So this is how they recommended. So they already recommended. So you might be using a different operation amplifier. So you need 2 operation amplifiers, and then this is your ADC ADS830. And then here they already said, see, when you look at it, see, this is, they are connecting to the non-inverting terminal, and then it is kind of a buffer. See, they connect the buffer, and then from here it's generating some voltage, and then that voltage is coming here, and then that is, so this is a scaling network actually. But then because this is operating in the inverting mode, so this is also an amplifier. So you can use this configuration. So when you are using this much configuration, the advantage is you are getting 2 blocks. One is the amplifier block, and then you are getting a scaling network. And then how it works? So that now that what we are going to do. So the idea is when you design so when you design voltage level shifter, amplifier voltage level shifter ADC, so then two ways you can design it. One is you design an amplifier using op amp, then you design a voltage level shifter, then you connect to the ADC. That is first one. Second one is combine these two, you got only one block, that is amplifier plus voltage level shifter. So voltage level shifter. So then you can combine it. So amplifier plus voltage level shifter, that is one option. So then you connect to the ADC. So then this is an option in the data sheet they have used. Then what idea they have used? So this is one way. You can also design amplifier, voltage level shifter, then ADC like this. But then another way is combining both. That's what ADC manufacturer said, not we said. So whenever you want to use ADC, please follow what manufacturer said. Then what I am going to teach you is why the manufacturer made such a diagram. Because manufacturer, those guys are experts in the circuits. So what they have done is a simple case. So you got an operation amplifier. So I am going to design an operation amplifier. Anyway, you have to design an amplifier. So what you are designing, say, an inverting amplifier. So when you design an inverting amplifier, you will be connecting to the negative. So suppose you are going to design non-inverting amplifier. So here they have used inverting, non-inverting. Yeah. So either it could be inverting or non-inverting. First I will take inverting, and then first I will get non-inverting, because we already said second is inverting. So there are two types of amplifiers. So non-inverting means you will be connecting your signal to the non-inverting terminal. Then how I will be connecting the feedback? Do you remember the non-inverting amplifier? Yeah, I will be connecting here signal, and then from here resistor, then coming here, something like this. So this is a non-inverting amplifier. How about inverting amplifier? Anyone remember inverting amplifier? So inverting amplifier I just now already shown. When you design the inverting amplifier, so you got inverting, non-inverting. So you will be connecting your signal to the inverting input, and then you got a resistor here, and then you will be grounding here. So this is an inverting amplifier, because when you connect something like this, it will be amplified opposite phase. If you connect something like here, it will be amplified in the same phase. So these are the inverting and non-inverting. Then when we studied inverting and non-inverting, we studied about the virtual short. Do you remember virtual short? So here if I am connecting, if this is 1 volt, here if it is 1 volt at time t1, then what is the voltage here at time t1? 1 volt, because op amp will make sure that. Then what is the voltage here? When you connect a signal, maybe this is also 1 volt is coming at time t1. So what is the voltage here? 0 volt. Why? Because it will make sure that these are matching. Suppose I am going to connect here 1 volt. Then what will be the voltage here? Zero. How many? 1. Yeah, because op amp will make sure that this is 1 volt. See, now you got an AC signal, but then here you are getting a DC offset of 1 volt. So this is a simple, level shifter. So you are getting level shifting and amplification, because this is a DC 1 volt. So here you are getting a 0 to maybe 200 millivolt input signal. So in the output what you will be getting is, so this is your output, and then this is the time. Then in the output it will be level shifted by 1 volt, because of here you are getting a DC 1 volt, and on the top you will be getting your inverted signal like this. So if it is something sinusoidal like this, it will be like this, because you are getting 1 volt offset. So this is a level shifter and amplifier. So it is a level shifter and amplifier, because when you plot the output, your output will be offset by 1 volt, because when this is 1 volt, this will become 1 volt, and then when this is 1 volt, nothing will go, current will not go through the operation amplifier, and then this 1 volt is connecting through the resistor and coming here. So you are getting a DC 1 volt, then this signal will be amplified, that also is coming through here. So that is the reason you are getting a level shifting. So this is the idea, you want to implement it. But then when you implement it, how will you connect here 1 volt? This 1 volt should be stable. Because whenever you connect to the op amp, you don't want this 1 volt fluctuating. And then because then this voltage will be fluctuating, that fluctuation again will couple to your signal. So you want a stable 1 volt. So that is the reason op amp and the stable 1 volt, you need to connect to the op amp. So that is the reason here if you check it, they already said you are that 1 volt, see how they are generating that volt. So they are getting some voltage that is from the ADC itself, that is called a reference voltage 2 volt. So ADC is giving you 2 volt reference voltage. So what do you mean the reference voltage? Reference voltage is whenever you want to generate a reference for ADC, like level shifting, ADC you will be connecting, here you will be connecting a power supply, see plus 5 volt, that is external power supply. But in the ADC they have got some very good circuit, and that will generate a reference voltage that will not fluctuate. Even if your 5 volt external is fluctuating a little bit, the ADC reference voltage will be constant at 2 volt. Means small fluctuations will not be affected. So that reference voltage we can use for generating a level shifting. See, they here what they are doing is, if you check the voltage here, what is the voltage? See, 1.25, because this ADC input range is 1.5 to 3.5. So that is the kind of range you are looking for. And then, so that is the reason, then how you are getting that voltage? So when you have 2 volt here, you are getting a 2 volt here, and then here what is the voltage here? It will be approximately definitely 2 volt, because here this is a buffer. Then a question for you, why people connect a resistor in the buffer loop? Usually buffer means this is a buffer, so this is positive, this is negative. Buffer means it is like this. Then why people connect a resistor here? Why somebody connect a resistor in the buffer loop? That is for the impedance compensation. So if you have some impedance issue, people will connect this buffer to make sure that it is matching with this impedance. So that is the reason they connect a buffer, some resistance here, that is for impedance matching with this, because here you are connecting an impedance and then you have to match it. So sometimes if people connect some value based on the, when they do practically make it, some issue will be there, then they will be recommending in the buffer for this particular op amp you connect this one, otherwise there will be an impedance issue, matching issue. So that is the reason in the buffer they recommended to connect a resistor here. Then if this is 2 volt, what is the voltage here? You can use a resistor divider. So then here it is 2 volt into 499 divided by 301 plus 499. So then you will get around 1.25 volt. So when you get 1.25 volt here, what is the voltage here? Yeah, 1.25 volt, and then whatever the AC signal is coming, that is riding on the 1.25. And then you are getting some gain, and then you have to make sure that that gain is within the specification. So you already got a voltage level shifter here. And then you got a low pass filter they recommended. That's how you should be connecting, and then it is going to the ADC. See, now you shifted to the required range. And then you have to make sure the amplification, everything is within that one. Now you already shifted it. Now you have to make sure that your amplifier is not amplifying above 3.5, because you already shifted your signal. So then because of this one, you don't have any headache. You can just copy the circuit and add it to your circuit, the DSO design. So that is the reason I have shown you here this circuit. See, here, then here you can see somebody added a capacitor, some value. Maybe because the simulation report, when they simulated some issue they found, then you may have to add some capacitor, that you have to figure it out. Whether you need some issue, if it is not meeting the specification, what you may be needing. You may not need this capacitor. As I said, you may not need this resistor. It's all because of the impedance matching issue. And then, so this part is going to the ADC. See, ADC we can't simulate. So this is going to the ADC. This is going to the ADC. So that is the ADC we already discussed in the block. So going to this ADC, see, this is going to the ADC here. Then what, the reference, so this part, see, we are using a standard voltage reference to create this, because when you have that ADC, see, they recommended how to get it. See, when you compare these two, how to simulate it. When you simulate, you don't have this part. How will you generate a voltage reference, this part? So how to simulate this one? So that's the reason here, then you can use a standard voltage source in the LT spice. And then here it could be the required voltage, this voltage. Then you can simulate it. Then this is the DC offset, and then it is coming, and it's coming to the ADC. So these all things you have to simulate in the LT spice, and then you have to submit the simulation report. So what is needed to be included? We already said, so how many of you saw the simulation report, the requirement? So this is a front end simulation, and then there are some things after simulating the circuit, means you have to get all these values. Then one more thing, last year some students didn't get a full mark, they got only around 60-65% for the simulation. Why? Because when you go to see, this is a one block, this is another block, this is another block, this is another block, you need to justify why you have connected these, what does the circuit does, you have to write what is the circuit, what it will do, why you have selected those values, why you have selected those values here, why did you, if you add a resistor, why did you add this one? Obviously you are designing, you know that you have to add it. So then again in this one you have to tell what is a guess, and then why you have designed a filter, what is this one, you have to write, oh, this is a Allen key filter, and then some values, any explanation, you added some extra value, extra capacitor, why did you add it? Because I got some spike, then I removed it by adding a capacitor. For example, in this one somebody will write, okay, I added this capacitor, you need some justification. And then here also you should be writing something about this block. This is a level shifter and amplifier, and then you should be thinking. Another thing what you have to do is your signal. If signal is something like this, at the end again it should be like same. If it is inverted, you need to add one more inverting stage in between. So you have to make sure that design. But then in this example there is no inversion, you can check it. So you have to write about each blocks, and then why the value is selected. Please add in the simulation report, because that carries some mark. Please don't just submit the simulation report. And then this is an example of a simulation report. So this one is somebody's simulation report. So there is a front page. In the front page you will be writing something like simulation report, core schematics and simulation report, something like this. First page, core schematics and simulation report, then the subject, your name. Then when you open it, you may have some content, something like this, LT spice schematics, then frequency and phase response graph of the low pass filter. So because low pass filter at ADC input, prior to the filter stage, input impedance graph, DC bias points, output waveform. So you can put different headings. This is an example. So these headings should be consistent with what is the requirement. Then I will show you an example how the simulation report looks like. So one report, what it looks like is, you can see here, maybe I can zoom and then you can see clearly. See, so the figure 2, what we need is frequency and phase response of the front end at ADC input. Frequency, see, then we want to see the frequency and phase response of front end at ADC input. At the ADC input, you should get these type filter characteristics. Means your filter that response, it is cutting off. You can see. So that is the kind of response we should be getting at the ADC input. See, at the ADC input, you have to be careful where it is. Then you also have to show some waveform. Another example is frequency and phase response measured at output clamp figure 1. See, so this one. So where is the out underscore clamp here? So if I go to my circuit in the one that I have shown you, yep. So this one, if you see out underscore clamp, so where is out underscore clamp here? See here. So when you measure here out under means after your clamping circuit, then frequency and phase measured, see, you should be getting something like this. And then frequency and phase response measured at out underscore div in figure 1. So that is here. Then input impedance graph. So this is the important one because filter one is easy. See, input impedance, when you measure the input impedance, you can see by varying that scaling network, because the scaling network is something like this, because somebody asked the question. So it is coming like this, one resistor, another resistor, ground, then you are getting a capacitor, then you are getting a capacitor, and then this output is coming. So this is the input. So by varying this one, you can get, see, 1 megohm, around 10 kilohertz it is coming, see, it is falling, something like this. And then how it is working? Why? Because the signal is coming, and then that signal might split up this point, some will come through this one, and then so how it is working is, I am giving you some idea. When the signal is coming, some part of the signal will come, and then it will be coming, and then it is a low pass filter. If it is coming this part, the capacitor is connected to the ground, low pass filter. But then if the signal is coming through this way, then it is a high pass filter. So it's kind of combination you can think of. By varying these capacitances, you can play with the impedance because of these two route available, and then you can get something like this. So these are the simulation report you should be submitting, like frequency and phase response of the filter. We already given you. These are some examples, and then this year we may add something new. But so don't look at the heading figure captions. But these are the some guidelines how you will be submitting. Like you have to plot it neatly, and then you have to submit it. Then you also have to write about each block, what this block does. And then for the simulation report, there is no confusion because you don't have to worry about this heading, because we will tell you where to measure it exactly, so that you can put the LT spice, you put the probe there to get the measurement and then plot it. Impedance, it should be at the input. Then for example, maybe this year we will say measure at this point, maybe measure at the buffer output. Then it is easy. You put the probe in the LT spice somewhere here, this point, and measure it. Maybe then you need to measure definitely at the filter output, because then only you will be plotting the filter characteristics. Excuse me. Then you also may have to plot in the output of ADC. So we will tell you where to do in the simulation report. So this is the first report you will be generating. So this is not a complex thing. Like with your knowledge, if you know LT spice, you can do it in like couple of three hours time. Realistically, you can finish your simulation report, because you know each block what it does. Now you have to justify some values, why you have selected, if you are adding some values, resistances, why you have added that value. For example, this resistance, why somebody added, maybe it was difficult to tune the impedance values in the required range, then I added this one so that it matched it. Or there was a spike, and when I added this one, I removed it. Excuse me. So that is up to the simulation report. You got a lot of time for the simulation report, and then we discussed the front end of the DSO. Now we will be discussing the digital part. So digital part we will discuss in the next lecture, and then today the remaining time what I will do is I will be discussing about again the analog part. Because analog part, when you design your simulation report, maybe it is good to know about anti-aliasing filter, or why we call low pass filter as anti-aliasing. So again we are connecting to our filter where we stopped. Non-ideal circuit operation or silent key filter. So non-ideal means when you design silent key filter, sometimes in the data sheet itself they will say, if you are using our op-amp for designing a filter, you may have problem like this. If you are designing a low pass filter, when you design simple silent key, something like this, you will have a cutoff then you will have a increment here. So what is it called? A 0, because this is a pole minus 40 dB per decade, then maybe this is another pole, your increment, you don't need this one. So their op-amp is basically what they are saying is their op-amp is crap for designing the low pass filter. But then they will say, they want to sell their product, they will say that you add one more low pass filter here, then you can make it flat. So that is called a non-ideal circuit operation. So that is actually not a good thing. Sallen-Key Butterworth filter with RC added in series with the output. So that is not a good design. So if you see some op-amp recommending, that is not good op-amp for the filter design. And in your case also, maybe you got only one option, use some op-amp, but then that is giving a cutoff, but then it is increasing something like that. A 0 is coming in the body plot, so then you can add another low pass and bring it flat. Then filtering ICs, there are so many companies, they are making National Semiconductor, Texas Instruments, Analog Devices, Linear Technologies. You will find so many ICs suitable for filter development. Then ideal versus non-ideal. It's a good idea to keep in mind the reality that no passive component is perfect. So when you design for something, there will be a little bit variation because you don't exactly get the value of your passive resistance or passive components such as resistance, capacitance, because you may need 2.19, you may be putting in realistically 2K. So there will be a little bit shift. In many cases, the non-ideal characteristics of your components will have a dominant effect at high frequencies, creating undesirable effects or simply no longer functioning as the intended component at all. So in your case, it is 20 megahertz. It is a low frequency actually. Megahertz is a low frequency, especially 20. Tens of megahertz is low frequency. It will work on a breadboard, in a good breadboard. So as a high-speed design engineer, I will not accept anything as high frequency below 1 gigahertz. So we take 1 gigahertz because when the parasitic effect come into picture, parasitic means when you have a resistor, you see only pure resistances, pure resistor, but it got capacitor and inductor value when it is coming to close to 1 gigahertz. And even in the capacitor, you will see inductor effect. All these things will come into effect. So that is called a parasitic. Even in the copper track, you will be seeing only the impedance, resistance value or the impedance value, but then it will have capacitance, inductance, all these values will come into effect of the copper track symbol PCB when it is close to 1 gigahertz. So that is called a parasitic components. Excuse me. Component tolerance will affect your corner frequencies within any frequency range. Then op-amp selection. So this is an interesting study somebody presented. So open loop gain, so which we already said in the data sheet, they give open loop gain should be 100 times, that is around 40 dB above the peak gain of a filter section to allow a maximum gain error of 1%. Means what it says is when you design a filter, sometimes you will have gain error. So when gain error is coming, whenever you have some Q factor, so whenever your filter got some Q factor, then there will be some gain error. So in your case, you don't get any gain error because you don't have any Q factor in your design. You are getting kind of flat. But whenever there is a Q factor, there is a possibility of gain error. In order to avoid that one, your open loop gain should be 100 times over the Q value gain. So what it says is this one. Your filter characteristics is something like this. Your filter got some gain because you are using operation amplifier, and then that gain, and then it is coming up. This is a Q value because whenever it is overshooting, and then this much is called a Q value. You know what I meant? The Q, we already discussed it. This is called a Q value, and then this is coming down. So this is your cutoff frequency, FP or FC. See, that's a cutoff frequency minus 3 dB. And then whenever design this filter, whenever you have to use, so this is a filter characteristics. And then if you are aiming to design something like this, so you want to design a filter something like this. So it's a low pass filter, but it got some Q value. And then you have to be careful which op amp you should be taking. Then what you need is, then you have to find out what is this value. And then this value then above that 100 dB should be your op-amp unity gain bandwidth. See, when it is plotting, there should be a 40 dB gap between this point and the unity gain bandwidth, the graph you have to check it. If you got 40 dB, that is kind of a rule of thumb, then your gain error is less. If this line is touching here, then you will have gain error problem. You don't get exactly like this. So these are some good rules of thumb. You might not be using, but better, it's good to understand these things. First order. Then they said, then how will you design this 40 dB? Then somebody converted. So if it is above 40 dB, then the line, your unity gain bandwidth will be, it is touching somewhere this point. Because then it is easy to find out. Because if you put a 40 dB margin, then you can find out what is the unity gain required for the op-amp. Then that is easy to find out. For the first order filter, unity gain bandwidth. So if your gain of this filter, see, if your this gain, whatever the gain you are getting, if you put in that value, and then if you know the cutoff frequency, see here, this is the cutoff frequency here, then it will tell you what is what op-amp you need, what is the unity gain bandwidth required. For second order design, if Q value is less than 1, this is the equation. If the Q value is greater than 1, this is the equation. So we will do an example, then you will understand. So this is the op-amp selection for filters. So this is a Butterworth filter, and then this is the first order, second order, third order. And then these are fourth order, fifth order, sixth order, and then these are the A values and B values, and these are the Q values. So this is available in the Butterworth coefficient. We are going to design a fifth order. We are going to design a fifth order. So we are going to a fifth order. So what is the fifth order here? You need 3 stages. A fifth order 10 kilohertz Chebyshev low pass filter with 3 dB pass band ripple. So the pass band ripple is 3 dB and a DC gain A0 of 2. See, that is the gain. The gain of Q, the DC gain of 2 has its worst case Q in the third filter section. So whenever, because this is a fifth order, for the fifth order we already needed 3 stages. So the worst case Q, that is in the third order section. So we have to pay attention in the third order. If you don't pay attention, you may get error. Then in the A02, so this is the Chebyshev low pass filter. Then you have to look at the Chebyshev low pass filter. When you are designing a fifth order filter, you have to find out the Q values. So for a Chebyshev filter, in the last lecture, if you see the filter chart, for the third stage, your Q3 will be 8.82, required one, and A3 will be 0.172. You can check the filter chart. In the third order, the Q values. Then you can find out what is the op-amp if you want to reduce the gain. If you want to reduce the gain error, then FT, if Q value greater than 1, because Q3 equal to 8.82, 100 into gain into FC by AI in the root of Q value minus 0.5 square, and then we are going to substitute 100 gain equal to 2, FC cutoff, what is the cutoff? 10 kilohertz, A3 0.172, then again Q value 8.82. Then we can find out what is the unity gain bandwidth required for your op-amp. So when you substitute, it is 17 megahertz. So that is the bandwidth you need if you want to make this design realistic with gain error less than 1%. Then this is for a Chebyshev low pass filter. If you find this, because you want something like this, see, your requirement is something like this, and then with a Q value. But then whenever you see higher bandwidth, then you can think of going for a different design. Different design means still we will be designing a fifth order filter, but then we will not go for the Chebyshev. Maybe we will see some other filter. For example, if we go for the Butterworth low pass filter with the same specification, but then the Q values are smaller for Butterworth. See, Q3 in the third order filter, the Q3 is 1.62 for Butterworth, A3 equal to 0.618. And then, so because Butterworth I already got the, see here you can see 0.61 and Q3 1.62 and then 0.618. See, Q3 A3 0.61 and then this is 1.62. For Chebyshev filter, this Q3 is around 8 point something. So that is the reason then you can go for a Butterworth filter and then your ft will become only 1.5 megahertz. See, for the same specification, but when you are using a different filter design, the unity gain bandwidth will be less whenever you have this Q factor issue. So this just for your knowledge, when you are studying this also you should be knowing. People might ask sometimes what is a gain error in the filter. Then gain error is we will be discussing mainly when you have a Q factor, because sometimes you may need this type of design. So what it shows is your gain bandwidth is less whenever you have Q value small, A value small. Just an example. So now we will start the comparator, because comparator is a very important part in order to design ADC, because ADCs, most of the ADCs, some designs means they use comparators. So what is a comparator, which I already discussed? A comparator is a specialized nonlinear op-amp circuit that compares two input voltages and produces an output state that indicates which one is greater. I already discussed a comparator in the beginning of the lecture. So this is a simple comparator. See, in the comparator what it says is you are putting some input voltage. It is a non-inverting terminal of the op-amp. Then the inverting terminal, what you did is you connected a voltage. So that voltage you are deriving that voltage using two resistors that is connected to a 10 volt. So this is 7 kilo ohm, 3 kilo ohm, and then you are getting say 3 volt here. So here this is your threshold voltage. We call it as a threshold voltage. And then the op-amp got power supply plus 10 volt and minus 10 volt. So if input equal to 0 volt, what will happen is you got 3 volt to the minus inverting terminal. So what is the voltage here? If V in equal to 0, what is the voltage? So you got three answers: 0, plus 10, minus 10. 0, how many of you? Plus 10, minus 10. So you got some other states then. That will be very interesting. Definitely it will be minus. Why? Because when your V in equal to 0, then your V out, which is equal to, what is the expression for V out? For the op-amp, it's maybe to start with whether this op-amp is operating in the open loop or closed loop. Open loop, how many? Closed loop. Okay, I'm very happy. At least nobody thinks that this op-amp is closed loop, because this is a simple case. See, this is your op-amp, and then what it says is here you connected plus 10 volt, minus 10 volt output, and then you are deriving some voltage from the supply, and then this is your 3 volt, and then this is your V in, and then this is the output. So your V out, this is the open loop. So comparator always operate in the open loop mode. So V out, which is equal to A0, that is a open loop gain, into V positive minus V negative. So if this is case, suppose V in equal to 0. So when V in equal to 0, that is equal to V positive, which is equal to 0. So which will become A0 into 0 minus V negative. So your V negative is 3 volt, and then A0 will be a very big value, and then which will become minus of a big value, and then means, so it will hit this voltage. So that is equal to minus 10 volt, because A0 will be maybe 1000. Usually that will be around 1000 in one case. Then it will become minus 3 volt. So it will become minus 300 volt. Sorry, minus 3000 volt, not possible. So it will hit this rail. So it will be minus 10 volt. And then I am going to draw it. So this is the input, this is the output on the same, and then so this is the input, this is the output. So your input is 0, and then this is the output. So output also is 0, and then this is a threshold voltage I am putting. So threshold voltage is equal to 3 volt. Then input I am increasing. So I came up to 2.9 volt. Then still, so what is the output? So up to this point, the output will become minus 10 volt. Up to 2.1, again minus 10 volt. But when it is crossing here, this point, when this V in, so when your V in equal to 3.1 volt, then what will happen is your V out will become A0 into 3.1 minus 3 volt, then you are getting a big positive value, so that it will, so then what happens is, so this is a comparator, and then when your V in equal to 3.1 volt, because your threshold equal to 3 volt, when this one becomes 3.1, then you can find out V out equal to A0 into 3.1 minus 3, then you are getting a very big positive value. So again, if gain equal to 1000, A0 is equal to 1000, you are getting around 3000 volt, means basically you will hit the upper rail. Then the comparator will, see your input voltage is coming here 3.1, then your comparator will shoot your output to plus 10 volt here. Again it will stay there. So the comparator is going, and then when your signal is again falling below the 3 volt, you are going to connect a sinusoidal volt in the input. Then what will happen is, again this point your comparator voltage is going below 3 volt, it will go to minus 10 volt. And then again it is going, and when it is exceeding here more 3 volt it is going. You know what I meant? So this is basically is a comparing a voltage. So it's a comparator. So using a comparator you can also convert a sinusoidal signal to a square waveform. So this is called a comparator. So comparator basically what it does is comparing the voltage at the input with respect to a threshold. You can decide what is the threshold value. So this we already discussed. See, if it is plus or minus 5, below 3 volt it will be minus 10. Above 3 volt it will be positive plus 10, and then whenever the input signal is going below 3, then it will come down. But then the problem with the comparator, so whenever you have a comparator, suppose this is your 3 volt threshold, and then your signal is going above, and then you got some noise which is fluctuating around the threshold. You know what I meant? So if you got some noise, what will happen is your comparator may go up, but then because of this noise it will go up and down. You got the issue with the comparator. So means here your input signal is sinusoidal, but then this one got some noise here. Then it will happen is this point you will not get one up, you will get so many up and down here, then it will go up if you got noise. And then the comparator will be going up and down because of this noise around the threshold. Again it will be going up, it is going down, it is correctly, again because this noise, again it is going up and down. So that is a disadvantage of a comparator, simple comparator. So whenever you have some noise, then the noise will make comparator going up and down, because that noise may be enough to push your threshold up and down. Then people started thinking that this is not a good way of making a comparison. Then they came up with the idea called Schmitt trigger. So then you may see in some circuit it's called a Schmitt trigger. So Schmitt trigger is the simple definition is a comparator with a hysteresis is called a Schmitt trigger. So we will study the Schmitt trigger. Sometimes the input signal to a comparator may vary due to noise superimposed on the input. The result can be unstable output. To avoid this, hysteresis can be used. A comparator with a hysteresis is also called a Schmitt trigger. The trigger points are found by applying the voltage divider rule. Then again, you are working, see, you are working in a company, you got this issue. They developed a comparator, and then you said the comparator is so great, but then somebody tested the comparator. Then what happened is here some noise is here on the top like this, and then it is like this, the noise is superimposed. When the noise here it is fluctuating, instead of 1 you will get going up, coming down, then it will stay here. You know what I mean? Then this became an issue. Then what you can do? So what you will think? Then they said, oh, you have to redesign the circuit because comparator is not just sufficient. So how will you solve this issue? Sorry, once again. But then because this noise you can remove using the filter. Sorry. Differential, how will you remove? Okay, so solutions are good, but we have to think of implementation. Yeah, differential can take away some noise. Again, filter can take away some noise, but still sometimes you can't remove the noise when you have some kind of the previously what I have shown is the noise will pretty much like the kind of a signal falling in the same frequency, but you don't want that is triggering. And so in that case, what you can do? So because this happens, why this is happening? Because at this point you got 3 volt, your noise is starting from 2.95 to 3.05. That is the range of the noise, and your threshold voltage is 3 volt. You know what I mean? So 2.95 your noise is starting, 3.05 your noise is stopping. You know what I meant? And then suppose I am making my threshold as a band, not one value. How about that one? So then I will make here the lower band is 2.8 volt, upper band is 3.2. So I am getting a band. So if this signal is crossing entire through the band only, it will be changed, so that the noise will be suppressed. So how can you make that band? So that is called a Schmitt trigger. So then people come up with the idea called Schmitt trigger, and then the band, this width is, they call it as a hysteresis. So that's how then people started. That's how they thought. It's no point in studying Schmitt trigger without understanding. So Schmitt trigger means it's a comparator with a hysteresis. The meaning is it's not having a one level. You are making a band, lower cutoff and upper cutoff. And then you can find out what is you can design a Schmitt trigger, and then so this is an example of a Schmitt trigger. So Schmitt trigger is your signal is connecting to inverting, but then you got a positive feedback. So Schmitt trigger is something with a positive feedback. Then you can create that banding, lower cutoff and upper cutoff, using these two resistances. See, then you can find out where is upper value, R2 by R1 plus R2 into V out. Lower cutoff, R2 by R1 plus R2 into minus V out. So then here your signal, see, is a varying, and then your signal is varying, then it is below. See, this is upper cutoff, this is a lower cutoff. So previously it's one line, at the moment it is a band. See, this is the band threshold. So that your signal is somewhere here, then it is here, and then when it is crossing the upper cutoff only, it will go to, see, below, and then again it is falling again in the band. See, nothing will happen. See, this signal is crossing this upper cutoff, it is coming lower the upper cutoff, it will not happen, because something to change, it should come below the band. Now it is a band, then it will go up and then stay there. So instead of one line, you are creating a band. So that is called a hysteresis. And then through positive feedback input, hysteresis is created, allowing for increased edge transition stability. So how it is? So when you have this one, so you can see here, see 4.765 volt. So that is a band you created. Okay, so when you have that band, you are getting a band using the Schmitt trigger, not one level. So this is the band lower value, this is upper band value. So it will not nothing will happen if something signal is changing in between this range. So that is the reason when this is crossing, see, it is crossing means your output changed, and it will stay there because the signal is falling below the upper value, not the lower value, then only it will change. See, lots of noise, nothing will happen, it is within the band, and then it is going up because again it is up value is there, and then again it's varying. When it is going below the lower band, yes, the transition happened, and then again it is varying within the band, nothing will happen. When it is going above the upper band, again the transition happened. So when you see, this is the output and then this is the input. So output is 5 volt, and then when the input is above the 5 volt only, your output is changing. See, and then when again your this state will become low when this is above, this is below 4.76. So that's the reason you are getting this width. When you plot output versus input, you will be getting this width, and then that width is equivalent of this width. So that is called a hysteresis. You know what I meant? And then for a comparator, what is the width of the hysteresis? 0. Yeah, because you don't get any width. Maybe I'll stop here and continue in the next lecture.
About the circuit of the amplifier and the level shifting. Where is it? Okay, now. Why it need the capacitor there?
Which one?
The capacitor.
No, it's for somebody's design. You know, we don't know why we put it. Because maybe in his design is different. You don't need that capacitor in the data sheet.
Okay.
So they put it because something happened in the design. Some spike or something came.
Okay.
When you simulate in the LT size, you will understand.
1K, the matching.
Which one?
How about the 1K? The 1K of the buffer.
Yeah, that the data sheet will tell you how much to put in.